Hi everyone, good evening.
Good evening, sir.
Yeah, so let's start the session. Give me 1 minute only. So yesterday we had discussion about the SVM and KNN, and we have already discussed about the logistic regression. So before I start the session, if you have any question, then you can ask me. All right. So we had talked about this KNN, SVM, and logistic regression. Let's talk about now the decision tree. So let me. Okay. So when we talk about this decision tree, so this decision tree is actually the supervised algorithm. When we say that supervised algorithm, it means it is also be used for doing prediction. Now, the beauty of this decision tree is that it can be used for the regression and classification both. Although this is usually used for the classification, but it does not mean that it cannot be used for the regression. And when it comes to this decision tree, then it is used actually the cart algorithm. Okay, it is used for the cart algorithm, and this cart algorithm is basically stands for classification and the regression. Okay, now second thing is that this decision tree consists of two words. One is decision, another is tree. So that means first thing, it's a tree-based structure. It's a tree-based structure. So when I'm saying tree-based structure, then obviously it will be represented somewhere like this. Okay, so this is the tree-based structure, and obviously this is the root node, and it has internal nodes. These internal nodes are called as basically these internal nodes that I'm talking about. These are the decision nodes or the internal nodes, and these internal nodes represent the features of the data set. What is the meaning of feature, everyone? So I'm talking about the columns. Here, the branches represents the decision rules. So whatever branches you are seeing here, they will be representing the decision rules, and whatever leaf nodes you are seeing here, they actually represent the outcome. Now, again, in another words, I can say that this entire decision tree will be having two nodes. One is decision nodes, and another is what? Leaf node. So these decision nodes are used to make decision, while the leaf nodes are just the output of these decisions. And another thing is that this decision node may have multiple branches to make decision. You see, just to reach to this leaf node, we have the multiple branches. So I can say that this decision tree is what? It's a graphical representation for getting all the positive solutions to a problem. Yeah, and that problem would be obviously depending upon a given condition. There might be certain condition or which this will be depending upon. Second thing is that we call it as decision tree. Why we call it as decision tree? Because similar to a tree, it always starts with root node, and it further expanded with the branches. And at last you can say that it constructs a tree-like structure. So whenever we'll have this decision tree, it will be asking a question, and based on the answer of yes or no, it will further split, and that tree will become you will split this tree into subtree. Okay. Now the question arises: we have already worked on the linear regressions, SVM, KNN. Then why we are using on this decision tree also? The thing is that when it comes to decision tree, it mimics the human thinking ability. Yeah. And while making a decision, it is easy to understand. And the second thing is that the logic behind the decision tree can be easily understood, because it is also shows a tree-like structure. Okay. So in this decision tree, we came to know about what? We came to know about this root node. We came to know about this leaf node. We now, the another term is what? That is called as split tree. And then the next one is called as branch or subtree. And we have pruning. As well as we'll have parent or child node. Okay. So when we are saying that root node, so I can say that it's a root node means the node from where your decision tree will be starting. And obviously, this root node is going to represent your entire data set. It is going to represent your entire data set. While I can say that this leaf node is what? It's a final outcome. Yeah. And so in another words, I can say that your decision tree cannot further split after leaf node. Once you have reached to the leaf node, you cannot further split. Next to this, we have this splitting, and splitting means it is the process of dividing the decision tree into subnodes according to the given condition. Yeah. Okay, and what is this branch or subtree? So whenever you'll be splitting your node, the tree that will be formed, it is called as branch or the subtree. Now, when it comes to parent or child node, so I can say that whatever root node is there, for example, this root node will become the parent for this, and in the another way I can say that this node will become parent of these. And we have very important term now. This is called as pruning. This pruning is what? It is the process of removing the unwanted branches from the tree. It is the process of removing the unwanted branches from the tree. And one more thing, guys, this pruning that we are talking about, it is the regularization technique for making your model right fitted. Because the problem with the decision tree is that it is prone to overfit. Suppose you're using any algorithm and that is not doing well, then means that is somewhere showing the underfitted, then you can try with decision tree. And in the maximum chances will be there that it will start behaving best right fitted. Okay. So obviously, whenever in this decision tree, you'll be trying to predict the class of a data set, then your algorithm will start from the root node. And this root node, it will be starting, and your algorithm will be comparing the values of this root attribute with the record attribute. And on the basis of that, it will follow the branches just to jump to the next node. And this process will continue, means in the same way for the next node, it will compare the attributes value and with the other subnodes, and it will move further. This process will continue until it will reach to the leaf node. Okay. So if I just tell you, so let me show you one example. Say that you have three features. You have three features. One is salary, another is distance, and another is cap facility. So suppose the root node that you got, it was salary. And you're saying that salary is between, say, $50,000 to $100,000. Okay, the salary is between $50,000 to $100,000. So obviously, okay, so obviously there will be two branches. One is what? Either yes or no. And actually, what is the use case here tries to understand everyone. So here basically, suppose that there is a person who got a job offer. Now he's in the dilemma to decide whether he has to join or not. Okay, so whether the offer should accept or not, we will be using this decision tree. So first of all, what is the primary condition? That the salary should be between 50,000 to 100,000. If the salary is in between is if the salary is in between 50K to 100K, if it is not there, means no is there. So that means you will reject the offer. And suppose the salary is there, the salary is in between the 50 to 100,000. So now you'll be talking about the distance, that whether the office is near to home. Again, either yes or no. So when again it is no, so you will just terminate, means you will reject the offer. Okay. And if the office is near to home, it is yes. So what will be done? You'll be trying to see the another option, that the cab facility is there or not. Okay. If either the cab facility will be given or not given. So if the cab facility is given, you will accept the offer. If the cab facility is not given, you will reject the offer. You will just reject the offer. Next. So you see here, suppose, say that we're just doing it. Salaries between 50 to 100K. Say that the salary was offered as 80,000K. So it means one condition is true. So you're going here. And suppose the office is not near to home. Office is far from the home. So obviously this, you just went here, but after this yes, you'll go to the no. And what will happen? You will reject the offer. But suppose the salaries between the 50 to 80, 100,000 K, and then the office is near to home, yes. They provide the care facility, yes. So the answer will be accepted, means yes. If say the salaries between 50 to 100,000, office is near to home, but they don't provide care facility. So that means again, he will reject the offer. So in this way, on the basis of the binary branches, the output will be predicted, the output will be classified. Next. So the question arises, whenever we'll be doing implementation. So while implementing a decision tree, the main issues arises that how to select the best attribute. Okay. How to select the best attribute, and this attribute is to be selected for the root node and the sub node both. And just to solve this problem, we have a technique that is called as attribute selection measure. We have a technique called as attribute selection measure, and using this attribute selection measure, we select the best attribute for the nodes of the tree. And just to do this attribute selection, we have two measure technique. One is called as information gain, and another is called as gain index. So these are the two things through which we can do the attribute selection. So let's come to this information gain. When we talk about this information gain, then actually we say that, or in this information gain, we can define it as that it is the measure of changes in the entropy. Yeah. So whatever change in entropy is there, on the basis of that, we just decide or calculate the information gain. Now, always keep in mind that the decision tree will always try to maximize the value of information gain. Yeah. And whatever node is there, whatever attribute is there, whichever will have the highest information gain, it will become to the root node. And this node will become split first. Yeah, and you know that in decision tree, first your decision root node split. So why this has becomes root node? Because this root node because of its maximum information gain or the highest information gain. And as I told you that this information gain is basically depending upon the entropy. So what is the entropy? Entropy is actually used to measure the impurity. Okay, if this entropy is used to measure the impurity in a attribute. Yeah, and if you want to calculate the entropy, so you know that the formula is what? Minus pi log of pi, rather I'll say sigma. So this is the entropy. And if I want to explore it more, then I can say that the entropy will be calculated if I represent it through S. Suppose whatever problem we are working with, it will have either yes or no. Its outcome will be either yes or no. So if I have to formulate this, then I can say that minus P of yes minus P of yes log base 2 probability of yes minus probability of no log base 2 probability of no. In this way, you'll be calculating the entropy. Okay. Another way through which you can build your decision tree, that is called as gain index. And I tell you, whenever you implement them in the machine learning, then the default is gain index. So here again, this is also used to measure the impurity. So when it is also used to measure the impurity, then my dear friends, obviously its value should be low. Yeah. So you can say that the attribute with the low gain index will be preferred as compared to the high gain index. Okay. So this is the basic concepts that we used to discuss in case of decision tree. Now let's see its implementation part.
Sir, the information gain is considered as root node.
Sorry?
Sir, does is the information gain considered as a root node?
No. The node which will have highest information gain will be considered as the root node.
Okay, sir.
Yeah.
Yes, sir.
Okay, so we have just read this data. Now, let's see this data first. So you see here, we have Five column, the user ID, gender, age, estimated salary, and the purchased. Okay. Now, so if you want to now we are just segregating our data into X and Y. Although when we had built on logistic regression, then we said that the gender will have some importance. Let's say that this gender don't have a importance. Although I told you that if you are in the dilemma that whether the this particular column is important or not, then the option that you have, you can do feature importance or you can do feature selection technique. Yeah. But suppose on the basis of my domain experience, I think that this gender column will not have any statistical significance while determining the purchase. So that's why what I did, I just considered the third and fourth column, the column at the index 2 and the column at the index 3. Okay, next. Now, if I describe this, my data set, then again you see that my data is suffering from a scaling issue in case of age and estimated salary. So what I'll do now, let me split this data into train and test, and I just did standardization to my X. Yeah. So whatever X data I had, I just did standardization to it, whether it was the train or whether it was the test. Now, you see here, I'm building this decision tree classifier, and just for that sake, we are from sklearn.tree, we are importing this decision tree classifier. Okay, and we are initializing this decision tree classifier in the classifier variable where the criterion we have taken as entropy. And my dear friends, if you want to explore this decision tree classifier, then you can just pass it in the help function. You see here, this is the decision tree classifier, and these are the different arguments that we have. And friends, if you see that the default criterion is what? Guinea. The default criterion is Guinea. All right. But here what we are using? We are using the entropy. Then you are doing prediction of the model on the test data. And you see the first list that you are seeing here. It is my actual Y. And this is my what? This is the predicted Y. Okay. Now, let me do prediction on the train data also. But the thing is that, so it should be what? It should be y1 underscore pred, and it should be y underscore train. Yeah. Okay, next. So let me build the confusion matrix of my test data. So here, while looking at this confusion matrix, what is your opinion, guys? What will be the accuracy score? Anyone? What will be the accuracy score? Anyone? How the accuracy score will be calculated?
the 61 plus 29 divided by the sum of total.
Obviously, yes, isn't? So that is 90%. 90% accuracy you got as a test accuracy. Let me check it out for the train accuracy. So you see here that the accuracy that you are getting now, it is what? It is the 100% accuracy. So do you think that any model will be giving 100% accuracy? That means what? Your model is overfitted.
Closer.
Your model is overfitted. So whenever your model is overfitted, then what you do, guys?
Regularization.
Regularization. In case of decision tree, the pruning is the regularization. And when we talk about this pruning part, then this pruning will have two types. One is called as pre-pruning and another is post-pruning. Okay, let's talk about this pre-pruning and the post-pruning first. So in the case of this pre-pruning, what happens? We we limit the expansion of decision tree during the in advance. Means we does not allow our decision tree to grow at its maximum. We always try to bound it. Yeah, we always bound the expansion of the decision tree during the model building. Means whenever you'll be doing pre-pruning, then your model will never grow at its maximum. While in case of post-pruning, what we do, in case of post-pruning, first of all, we allow our decision tree to grow at its maximum, and then we just prune it. Okay, everyone. So in the case of post-pruning, first of all, our decision tree will be grow at its maximum, and then after we'll just prune it. We'll just limit its growth. Okay. So again, when it comes to pre-pruning, so it's basically here we do hyperparameter tuning. We do hyperparameter tuning in case of pre-pruning. So if you want to do hyperparameter tuning, then first of all, you should know that what are the different hyperparameters we have. Okay, so before that, let me upload this pre-pruning part. Let's set this one. Okay. Suppose I just read this data, the movies.csv. And here, first of all, just look at this data. So if we have these features that like marketing expenses, production expenses, movie coverage, the budget, movie length, on the basis of that, what is my box office collection? So when you look at this box office collection, what is your opinion, guys? Will it will be using classification or regression? Everyone, please tell me. On the basis of this, why? What do you think? The regression will be applied or classification? Anyone? So your classification or regression always depends upon the kind of Y we have. And here, this box office collection is what? It is the continuous. So whenever you will have continuous data, then what will be applied? The regression will be applied. So whenever you will be trying to apply regression using decision tree, it will be decision tree regressor. Whenever you'll be trying to apply the classification, it will be decision tree classifier. Okay, now so again you see here out of the features, this 3D underscore available and the genre, they are the text data. And you know that the genre will have impact on the box office collection. This genre will have impact on the box office collection. So guys, these two are given in the text form. These two are given in the string data. You see, genre is thriller, drama, comedy, and the 3D underscore available is yes, no. So whenever they are the text data, then we need to convert them into numeric. So how you will do that, everyone?
One hot encoding.
Yeah. So it will be done on the basis of the one hot encoding. All right. So and you know that the one hot encoding is done on the basis of the pd.get underscore dummies. So you see here that we are applying this pd.get underscore dummies on our data, and this will be applied on these two columns. Now you see that the one hot encoding has been done. Next. Then we are just segregating our data into X and Y. You see, this is my X and this is my Y. So you see in the X, we are keeping all the columns except what? Collection. Next, let us split our data into train and test. Okay, let us split our data into train and test. And first of all, you see here what we have done. So okay, so you see here, whenever it comes to the decision tree regressor, what is the criterion? That is a squared error. It could be squared error, mean squared error. Yeah. So the default is squared error. Then we have lot of hyperparameters, like what could be the maximum depth, what is the minimum sample split. So what is the minimum sample split? That after splitting your node, at least how many samples should be in the node. In the same way, we have minimum sample leaf. So what I mean to say that there are a lot of hyperparameters and they have their default value. So just to do regularization, just to do pre-pruning, what we'll do before or at the time of the model building itself, like here you see that we're building this model. At the time of the model building itself, we will do some hyperparameter tuning. For example, you see, we have limited that the maximum depth to this decision tree will be 4 only. And then we just train this model on the trained data. So if I show you this graph, so for that, we are using this matplotlib, and through this tree.plot underscore tree, we are representing this decision tree. You see? So friends, here what we have done, our maximum depth is 4. So even during the at the time of the decision tree model building, we have decided it that the depth will be 4. Now, say that we are not deciding it. We are not deciding now. We are completely building the decision tree. We'll have to wait. Since it is under process, so we'll have to wait. You see? So actually, this was the decision tree. Actually, this was the decision tree. But you know, during the time of the model building itself, you just limit its growth. You have not allowed your decision tree to grow at its maximum. And just because of that, so this is the example of the pre-pruning. So here what you did, you just did one hyperparameter tuning. So you just played with the maximum depth. What is the second option? Second option, let's say that, so you're just, doing prediction on the test and train data. And let's see what is the R2 score of my test data. So the R2 score is what? 67.2%. Let me check on the train data also in the same way. You see here, the train accuracy is 89.26. The test accuracy is 67.20. So what is your opinion, guys? What kind of model we have? Anyone? So obviously the model is overfitted. The model is overfitted still. So let's try with another thing. And what we have done now, we have minimum sample speed equals to 4. So what we are doing now with the another part, and then again we are building the model. We are doing prediction on the test data, and let's calculate the RT score for the test data. And you see, now when we fixed minimum sample speed equals to 4, then it has becomes 0.539. And if I check it out on the train data, then you see it is 99.4. Means even In comparison to this, your maximum depth was somewhere doing well, but still that was also overfitted, and this is also overfitted. Okay, let's do one thing. We'll be trying with the minimum sample leaf. All the things will be same, only this minimum sample leaf value we have changed. You see, the test accuracy is what? 62.3. And if I talk about the strain, so it is 96.0. So when we were trying with the single hyperparameter and we were tuning them, still whatever model we are getting, it is overfitted. So what is the next part? Let's take some combined hyperparameter. So you see here, in this model, we are having max depth equals to 7, minimum sample speed equals to 3, and minimum sample leaf equals to 3. So now you see that instead of working with the single hyperparameter, we are working with the 3, and all the process will remain same. So when we test the model, it was 63.6. And if I talk about the train accuracy, so it is 94.11. Although in comparison to others, in comparison to others, this is working well. But still what is there? My model is overfitted. So sometimes it may happen that you're trying with the multiple permutation combination just to do hyperparameter tuning in terms of this pre-pruning, but the problem is that you're still getting the model overfitted. So what is the solution? Whenever you will not be able to get the right fitted model using pre-pruning, you should try with the post-pruning. And I tell you one thing, whenever your pre-pruning is not working, try with the post-pruning, surely it will work. Okay, surely it will work. Okay, so this is about the pre-pruning. Now, let's talk about the post-pruning. So again, for the post-pruning, I show you one thing. You see here, there is a parameter yeah. There is a parameter called as CCP underscore alpha. Yeah. This CCP underscore alpha is what? It is the penalty term or the impurity. So whenever it comes to the post-pruning technique, so what exactly we do? We just first allow our decision tree to grow at its maximum. Then we start adding impurity to it. And this impurity is known as CCP underscore alpha. Now let me show you. You see, so this CCP underscore alpha is there, and This CCP underscore alpha is actually used in the cost complexity pruning path. And this cost complexity pruning path is the function that will be using the CCP underscore alpha. And what is the purpose? The purpose is that whenever will be adding this CCP underscore alpha, what will happen? When at each value of this CCP underscore alpha, some impurities will be added. Yeah, and just because of this impurity, what we will see that your train accuracy and test accuracy, your train accuracy will be decreasing and your test accuracy will be increasing. So we'll be finding out that appropriate value of alpha at which the train accuracy and test accuracy is very high and they are very close to each other. So this is the job of the CCP underscore alpha, which is the impurity. I hope you understand, everyone. Now, you just see here, so whatever library we are using, that is fine. For this, we are using the inbuilt data, that is breast cancer data. Okay. So this is the data that is already in the sklearn. So we are going to use this. Now, let me load this breast cancer data in terms of X and Y. Yeah. And whatever data will be provided to this X and Y, it will be in the array form. So what is our primary responsibility? The primary responsibility is just to convert them into data frame. And now if you see the shape of this X1, see it is having 569 rows and 30 columns. Then we are just splitting our data into train and test. And then we're building this classifier model and training on the train data. So let me show you this decision tree. So for that, we are using this tree.plot underscore tree, the way we have seen in the decision tree. You see, actual decision tree is this one. Actual decision tree is this one. So right now, whatever decision tree you are seeing here, it has grown at its maximum. Now, let me do prediction on the train and test. And on the basis of that, if you see the accuracy score of the train data, so it is 100%. The moment you are getting 100% accuracy, it means your model is overfitted. Yeah. It means your model is overfitted. So what we will do, you see here, we will be taking this, calling this cost underscore complexity underscore pruning path. That is the function of the CLF. And then we'll be using it to apply on our train data. And now if you see this path, so you see, these are the alpha value. And these are the impurity corresponding to the alpha value. Means when the alpha value is 0, the impurity wasn't added. When the alpha value was this one, then this much of the impurity or the error is being added. Now, So here, what I'm trying to see will be doing first, what is the CCP underscore alpha and what is the impurities. And that will be getting from path.ccp underscore alpha and path.impurities. Okay. So this is again, whatever we had seen earlier. Let me show you in the form of data frame that will become more clear. So that is why you see, we have made this dictionary where the key CC alphas and this is the value that we were getting. This is the impurities and we were getting the impurity. So, when this is the alpha, then this is the impurity added. Okay. So suppose the training accuracy is getting 100%. What will happen? It will be adding this much of impurity and it will become what? 100 minus 0.004. That is, yeah. So you see here that when this impurity will be added, the magnitude of the input parameters of the trained data will get decreased, and just because of that, your train accuracy will be decreasing. Now here, what exactly we are doing, let me show you. Say that this is my code. So suppose here, what we are doing, we are first of all taking an empty list. We are taking an empty list known as CLFS. Then we are taking a loop variable CCP underscore alpha. And why we are taking it? Because the CCP underscore alpha will be picking one by one the value from the CCP underscore alphas. And now we're building this model, this entry classifier, where the CCP underscore alpha will be varying one by one. Suppose first time, what is the CCP underscore alpha? That is 0. Yeah. So this model will be built. It will be trained on the trained data, and you'll be getting the value of the CCP underscore alpha and the proper impurity. Now what will happen? In the next time, the CCP underscore alpha value will change. And what it will become? It will become, no, not 1, this one. You see? So that means what? Your model will be running for how many, this loop will be running for how many times, dear? It will be running from 0 to 12, means 13 times. Yeah. This loop will be running for 13 times, and for each value of the alpha, the impurity will be added. Yeah. And your train and test accuracy will become change. So for example, let me
So
show you.
why 13? I didn't get it.
By 13. See, this is starting from 0. This is starting from 0 and it is up to 12. So how many alpha values are there? 0
Yeah,
to,
that is fine. But how it is running till 12 times? So that's what I want to like.
I didn't get your question.
So how this how what we add in a code, so it's running till 13 times. So just want to know why it's 13.
Basically,
So how it's compared?
you had this cost complexity pruning path. Okay. You just consider this a function, but you can consider it as the model also. So when it comes to this cost complexity pruning path, Okay, so you see here, uh, so we are using this CCP underscore alpha, that is non-negative float value. The default is 0.0. So this complexity parameter will be used for what? Minimal cost complexity pruning. And the subtree with the largest cost complexity, that is smaller than CCP underscore alpha, will be chosen. By default, no pruning is performed. Okay, this is the explanation it has given. Now let me tell you another. So when it comes to this complexity pruning path, which is actually responsible to perform pruning, this minimal complexity pruning, it actually, whenever you'll be doing regularization, then there will be the alpha. This alpha is actually the penalty term. It penalizes the model. So this alpha will be penalized. It will be parameterized by more than or equals to 0. And this is known as actually the complexity parameter. Now, so in this I can say this cyclic version that we are talking about, no, it actually try with the 13 value of the alpha. Okay, just try with the 13 values of the alpha just to get the what I say, the right fitted model. And one more thing, why 13? Because according to this, whatever you'll be using, this 13 alpha value will be more than sufficient. Because ultimately, what is your aim? Your aim is to get the right fitted model. Yeah, your aim is to get the right fitted model. So for that, this 13 value of alpha is more than sufficient. Okay. Now, when we are applying this train score now, so this is that. And if I go with this test score, now let me do one thing. What I'll do, I'll just create a data frame where I'll have the alpha, the corresponding impurity, and the corresponding train and test score. Okay. So you please just have a look here. So why 13 value of alpha? Because this is the number of iterations decided by the cost complexity pruning path function. Now, even if I see that when the CCP underscore alpha value is this one, this much of the impurity is added, and just because of that, what has happened? Your training accuracy has becomes 99.76, and the test accuracy has becomes 88.81. Now, friends, when you just look at here, out of this total parameter, where you find that the train and test accuracy, they are very good, and the difference is very minimum. Can you tell me that index number? I think that will be somewhere 7 or 8. Because you see, 99 minus 0.88, it will be somewhere 9%. Here it will be 9%. Here it will be 9, around 9, around 5, around 4, around 4. Here it will be around 3, isn't it? So according to me, At the 7, we'll be getting the right fitted model. But you can check it out in another
But
way.
sir,
Yeah.
but at the 13th point we have 0.
Where?
13th, sir, 12.
12. But you see, will you accept this much of accuracy? See, we have to think, we have to take care of both of this. First, your accuracy should be very high. Your train and test accuracy should be very high and they should be close to each other. Although here the difference is 0, but you see, what is the accuracy? It is only 62%. And here what we are talking about, it is 97 or 96% accuracy. Getting my point? And that is why we will not consider this 12, because the accuracy is really very low. Okay. So let me do
Sir,
one thing. Let me plot the
excuse me,
plot.
sir.
Yes.
Sir, could you please repeat? I didn't get it.
Okay. Let me tell you. See, first of all, what is our agenda? We have to get the high accuracy. We have to get the high accuracy. So is there any difference? Is there any much difference between the 97% and the 96%?
No, sir.
Okay. Now, suppose the train accuracy you are getting 97% and the test accuracy you are getting 91%. First thing. Second thing is that, say, the train accuracy you are getting 95% and the test accuracy you are getting 93.5%. Now, which model you'll choose? This one or this one?
So the lower one.
Lower one. Why? Because
Yeah.
here
So because
also
there is less difference in the accuracy.
exactly. And that is why I just denied that we cannot choose this 12 number.
Okay, sir. Got
Although the difference is 0, but accuracy is really very low.
it. Got it, sir.
Yeah. Now see here what we are doing. We're plotting 2-line plot. One where we'll have this alpha and the train scores. Here we'll have the alpha and the test scores. And let me plot this plot. So this is my plot. Okay. You see. So if I look at this graph, what is your opinion, everyone? Where, see, first of all, this blue is what? Train accuracy. And this orange is what? Test accuracy. So you just have to see at what value of alpha we're getting the right fitted model where the train and test accuracy both will be very high. Okay, suppose if I consider this point, at this point, what is there? The accuracy of the train is somewhere 99, but corresponding to this, when you will consider, then you see the gap will be up to 8%. So not consider this. Guys, make me correct if I'm wrong. If I consider this one, and you see here, the train accuracy is somewhere, this one, and it is, what will be the accuracy? This is a gap of 5. So the gap of 5%. I think it will be somewhere 93% or 93.5%. Isn't everyone? So somewhere take this reference where the train accuracy is 93%. Now, according to this, what is the test accuracy?
91.
91 or 92? I'm not sure. Let's consider as 91 or 91.5. Okay. Yeah. And corresponding to this, what will be the alpha value? It is somewhere, I think, coming between 0.0 and 0.05. I think it is coming the middle of this, isn't? So if I draw this, yeah. So it is somewhere, I think it is 0.025. So let's see where do we have any 0.025? Yeah. Or, so according to this, I think this is the value, no? 0.00. So according to this should be there. So the middle should be what? It should be 0.025 or 0.0025. Everyone? It should be 0.025 or 0.0025.
0.025.
0.025, no? Since it is coming in the in between. So what we will be doing? Let's see here. But the thing is that, okay. Anyway, so here you see what is the value we are getting? 0.023142. But what, according to me, you know, whenever you'll be looking at the graph, we are getting the lump sum value. So instead of this 0.025, what the value we have taken? 0.023142. Now I think you understand why we have taken this. So where this value is, yeah. And even if you are not able to understand it, then what you can do, you just count it. So 1, 2, 3, 4, like here it will be there. So let's see, let's consider as 0.025. So when you are considered as 0.025, okay, and you are building the model. Yeah, we got this. Now, on the basis of that, if you see the test accuracy, so what is the test accuracy? It is 91.6. If you remember, guys, if you were seeing here, then you know that was somewhere around 91. So it is telling 91.6. And what is the train accuracy? So the train accuracy is 93.19. So we are at the right track. Yeah. So this is our right fitted model. And second thing is that if I see the decision tree after the pruning it, because now we have applied some alpha value here. So this is our decision tree. After doing this post pruning, this is our decision tree. So I hope you understand what is the decision tree and how do we do this regularization technique in case of decision tree. And that is your pre-pruning and the post-pruning. So this is all about the today's session. If you have any questions, then you can ask. Okay. All right then. So I'll just share this code and the data. We'll share the assignment also. Please work on it. And suppose you're working on the data and the model is overfitted, then try to work with the pre-pruning and post-pruning both. Okay, everyone. So let's just stop here.